Good morning, everyone. Let's get started. So in the previous classes, we've studied a lot of problems in source coding. We started off with lossless source coding, and then we saw a little bit of lossy source coding, as well as multi-terminal lossless source coding, or the Slepian-Wolf problem. Right? So from now on, we'll exclusively look at channel coding problems. In particular, we'll see two classes of channels, the multiple access channels and the broadcast channels. And these, in some sense, model both the uplink and the downlink transmissions in, for example, cellular systems. Right? And these are sort of the most basic building blocks of any multi-user channel coding scenario. Right? We'll see that at least the sort of multiple access channels which study, these are kind of well understood, and we know what the optimal rates of communication are. But then we'll see that once we come to broadcast channels, a lot of things are still open. We still don't have a complete understanding of that particular problem. All right. So before we start with multiple access channels, are there any questions from the previous classes?
Sir,
Yes.
in the last proof, like we have done for the converse, no, sir.
Yes. So just give me a minute. I'll try to bring that up. Right. So this is what you wanted, right?
Yes, sir. So here, will we not check for the achievability thing?
Okay, so I didn't do the proof of achievability, but then you can prove an achievability proof using. I mean, so I have outlined the proof of achievability over here, but again, in the interest of time, I won't go through this. But I can always maybe create a separate recorded lecture, or we can have a separate lecture talking about the achievability proof for the rate distortion theorem.
Okay,
All right.
okay, sir.
So I believe, think the notes up on Piazza should have the achievability proof. So you can just take a look. Uh, Essentially, the ideas are pretty similar. So that is why I didn't go through it once again. But we can always discuss this. So just go through the achievability proof, and then if you have any questions, we can always discuss them in the next class.
Okay, sir.
Right? Any other questions? Okay, so multiple access channel is basically the sort of model you would see in uplink transmissions of cellular systems. So for example, you have a number of cell phones which are connected to a single base station. So so basically maybe you have say 10 cell phones which are currently connected to the base station near IIT Hyderabad, and and now essentially all these 10 users, when they want to say send upload data to the base station, this could be either voice or say text in the form of SMS, or it could be say internet data, right? Maybe you're uploading a video or a picture. So all of them are making use of a common channel in order to communicate through a base station. So essentially, the base station needs to distinguish between the data sent by each of the 10 users, and then this is of course later sent through the core network to another base station, which is then sent to some users which are geographically really far apart, right? But these 10 users are physically close to each other, and they're making use and they have to communicate to the base station, right? So this is the basic model for a multiple access channel where multiple users are in some sense sharing a common channel to communicate to a single receiver. So you have multiple senders but a single receiver, right? So the most common, say, example that you see is for example, if you're in say some kind of a social event where there are multiple people talking to one particular person, or even in class when when say multiple people try to answer one particular question asked by the teacher. Essentially, all of these are multiple access channels, right? And in general, if there are say 10 people who are talking at the same time to one particular receiver or one person, you know that it's difficult for that person to distinguish between like what is spoken by whom, right? So so that is really the challenge in communication over multiple access channels. We'll see how one can actually communicate. So one obvious way of communicating is that if you have 10 people who want to uh, tell something to one particular person, then the most obvious strategy is to is that only at any point of time, only one person speaks and the rest of them remain silent, right? So if you have k users who are trying to talk to one particular base station, then one obvious approach is that maybe for the first 10 seconds user 1 talks whereas all the others are silent. For the next 10 seconds user 2 talks to the base station while the rest of them are silent, and so on, right? And you can do this in a round robin fashion. So this is what is called say TDMA, time division multiple access, and in particular we'll see that this is, while this is a strategy, it's a simple strategy to implement. It is not optimal, and this is something we've also seen in the very first class where I showed that TDMA is not optimal, but there's something else you can do, something better that you can do. And we'll investigate that in more detail. We'll see it more formally. And we'll show that TDMA is in fact suboptimal in general, and you can do something much better. Okay, so but before that, we need to first set up the problem, and although it should be straightforward at this point, let's do it more formally. All right, so the class of multiple access channels that we will study in this course are what are called discrete memoryless multiple access channels. So both are important in this setting. It's discrete, which implies that the alphabets are discrete and the channel is memoryless. So in some sense, the way the channel corrupts different symbols is independent of the way it corrupts the other symbols. Okay, so let's look at it uh, in detail. All right. So any channel is basically a probabilistic map from the inputs to the output, right? So if so in a multiple access channel, there are two users. So in a two user multiple access channel, there are two users who want to communicate to a single receiver. There are two senders and one receiver, and we assume that time is slotted. So it's a discrete time system where communication happens over n time instants or n channel uses, and and so each user can send essentially a vector uh, of length n coming from some alphabet. So we'll assume that x1 n comes from some script x1n. It could be something, it could be very general. As long as it's discrete, it is fine. And x2n is the vector sent by the second user, and we assume that this comes from some other alphabet script x2. So these are sent to the channel. Uh, so these are the inputs. So the inputs to the channel are x1n and x2n, and given x1n and x2n, the channel outputs some random vector yn, where yn comes from some alphabet script y, right? And so the channel is essentially a random map from which takes as inputs x1n and x2n and outputs a random yn. Right? So, and the channel is said to be memoryless if the following happens. So, p yn given x1n x2n and x2n. So the probability, the conditional probability, the conditional PMF of yn given x1n and x2n essentially factorizes as a product. Right? It is some py given x1, x2 of y of I given x1 of I, x2 of I. Alright, so this is this. So we say that the channel is memoryless if this happens. So essentially, you're transmitting components x1 of 1 up to x1 of n. User 2 transmits x2 of 1 up to x2 of n. So n symbols. The receiver gets y1 of 1 up to y2 of n. So given x1 and x2, y1 of 1 is independent of all the other components. y2 of 1 depends only on x1 of 2 and x2 of 2 and is independent of all the other components, and so on. Right? So that is when we say that the channel is memoryless. So our goal, of course, is to communicate some useful information across this particular channel, and one way of doing this is that, so you have user 1 who wants to send a message of length kn. So user 1 wants to send k bits through this channel, and user 2 wants to send, say, L bits through this channel. Right, and we'll assume, so again we need a probabilistic description of the messages. We'll assume that both M1 and M2, the two messages, are uniform. So user 1 has a sequence of kn IID uniform random bits, and user 2 has another message of length ln, which is again assumed to be uniformly distributed. So you have ln IID uniform bits, and these need to be communicated. So the receiver observes the output of the channel and then has to make an estimate or a guess of what M1 and M2 are. Right. So for this purpose, we what does each user do? Each user encodes its particular message to a code word or a sequence, and then transmits it across the channel. The receiver observes the output of the channel, and from this makes a guess about what M1 and M2 are. All right. So the goal is to design these encoders and decoders such that the messages are decoded as correctly as possible. So, so we want to ensure that the probability of error, which is the probability that either M1 is decoded incorrectly or M2 is decoded incorrectly, this is vanishing in as n tends to infinity. At the same time, we want to ensure that we can transmit as many bits of useful information through the channel as possible in n channel uses. So we'll say that Kn is n times R1 for some uh, positive number R1 independent of n, and Ln is n times R2 for some R2 which is some positive number independent of Ln. And R1 and R2 are the rates of user 1 and user 2. Right? And we'll say that for a given multiple access channel, for a given two user multiple access channel, we say that a rate pair R1 comma R2 is achievable if you can construct sequences of encoders and decoders which encode n times R1 and n times R2 bits respectively to code words of length n, such that the probability of error is vanishing in n. So the lim sup as n tends to infinity of the probability of error should be equal to 0. All right. So if this happens, we say that a pair R1 comma R2 is achievable. All right. And our goal is to understand what all rate pairs are achievable for a given channel. Right. So unlike the point-to-point case where we had a perfect ordering, so we wanted to make sure that the highest rate is achievable. When it comes to two users, you can't really say what the best rate pair is, right? So it's possible that one rate pair is good for one user, but it's slightly worse for the other user. And we'll see that in just a little bit. All right. But so far, are there any questions regarding just the setup itself?
Sir, am I audible?
Yes.
Sir, as we are considering time sharing, like if it is time sharing, then do we really have to consider py given x1 comma x2? Like because it will be different time slots, then can't we consider different for different users? Like why are
No.
we joining?
So this channel is completely specified, right? So time sharing is one particular scheme, and we'll investigate that in just a couple of minutes. But but this is the system. This is given to you. You can't make any modifications to the channel. All right. And it's fairly general, as we'll see. We'll see a couple of examples in just a couple of minutes. But throughout, for all the n channel users, the channel behaves in an identical fashion. The corruption that is performed by the channel is always identically distributed.
So we are not considering the time sharing currently.
So we will see time sharing. So time sharing, as I
Okay.
mentioned, is a scheme, right?
Okay.
So right now what we have is the channel, right? So for
Yes. Sir.
example, one particular channel is the following. So yi, so let me call it y of I is x1 of I plus x2 of I plus z of I, where z of I is some noise. For example, it could be Gaussian noise. Right? If you wanted to complicate it a little more, you could say that is h1 x1 of I plus h2 x2 of I plus z of I. Right? So this is for I equal to 1, 2, 3 up to n, this is how the channel behaves. And that is exactly what I mean by py given x1, x2. Right? So for each channel use, this is exactly how it behaves. Now what you send as x1 and x1 of I and x2 of I are dependent on the users. It depends on the system designer. But this particular channel is given to you. You cannot make any changes to this. And that is
Yes.
what I mean by py given x1, x2.
Yes, sir. Yes.
All right. Good. Any other questions? Okay. So, all right. So our goal is to really understand that, understand what rate pairs are achievable, right? And we'll say that the set of all, the closure of the set of all achievable rate pairs is what we call the achievable rate region or the capacity region. Okay? And so our goal is to understand what the achievable rate region is. Okay. Now, even before we proceed, let's forget about the claim for now and see what can be achieved. Right. So as I mentioned, one of the simplest things to do is time sharing or time division multiple access. Right? So let's see what we can achieve using time division multiple access, in which one user remains silent for some time, for maybe some alpha fraction of the time. User one, let me put this in a separate. So we have time division multiple access, wherein, say, user one is active for maybe alpha fraction of the time. So maybe alpha n channel uses. Right, for some alpha between 0 and 1. And for the remaining 1 minus alpha n channel uses, user 2 is active. So when user 1 is active, user 2 is silent. And when user 2 is active, user 1 is silent. All right, and we'll see what it means for a particular user to be silent or active. All right, so let's say that we split the n channel users into two parts. Okay, so this is alpha n, and this is 1 minus alpha n. Okay, so remember that each user has to send some particular symbol. So for each channel use, every user has to send something or the other. All right, so you're given py given x1, x2, y is in y, x1 is in some alphabet x1, x2 is in some alphabet x2. Okay, so what does it mean for one particular user to be silent? Well, one way to do it is that whatever the user transmits is something fixed. Okay, it always transmits something, some fixed symbol, which is independent of the message it has. Right. So by active, maybe user transmits whatever x something, x alpha n or x 1 minus alpha n, depending on, so user 1 sends x1 alpha n, user 2 sends x2 1 minus alpha n, which depend on the actual message. All right, so what does it mean for someone to be silent? The user transmits the same symbol. So user transmits some symbol x right, all the time. So for all the alpha n channel uses, or for the 1 minus alpha n channel uses that it is silent, it always transmits one particular symbol, and this symbol is known to everyone. It is known to user 1, it is known to user 2, and it is known to the receiver, and it's decided beforehand. So for example, let us consider the the say, let's say, Gaussian MAC, or the additive MAC, as we've seen earlier. It doesn't have to be Gaussian. So in the case of, let's say, the additive MAC, maybe the user 1, so in this case, say script x1 comes from, so maybe this comes from some constellation, let us say, so yeah, so in one case it could be R, comma x2 equal to R. So both user 1 and user 2 transmits a real number in each time instant, and the received symbol is also some real number, right? And y is equal to, so y of I equal to x1 of I plus x2 of I plus z of I, right? So maybe when the user is active, then it transmits some particular code word. When the user is silent, maybe user sends 0, right? The silent user transmits 0. Right? So in the first alpha n channel uses, so right, so the user 1 sends some sequence of symbols. So this is what the signal sent by user 1 would look like, whereas what user 2 sends is something is all zeros. Then for the rest of the 1 minus alpha n channel uses, user 2 is going to remain silent, whereas user 1 is going to remain silent, whereas user 2 transmits some particular code word. Right, so this is one particular example of time sharing or time division multiple access, right? But note that it doesn't have to be the case. So when a particular user is silent, it doesn't necessarily have to transmit all zeros. Right? It really depends on the problem and what the constraints are. So maybe suppose that x1 and x2 are real alphabets, and instead of being real alphabets, maybe x1 and x2 are supposed to be BPSK. Okay, so it always has to be either +1 or -1, say. Okay, and the received vector is always a real vector. Okay, so now maybe the silent user doesn't have to transmit all zeros. For some, we could have some kind of constraint, right? Again, depending on the problem, but maybe the silent user always transmits -1. Okay? So in this case, what would the transmissions look like? So user 1 always transmits whatever the message is, right? Whereas user 2, it always transmits -1s. right? And in the next 1 minus alpha n channel uses, user 1 transmits minus ones, whereas user 2 transmits some particular code word. All right, so as part of the system design, you allot some particular symbol which you call the silent symbol. Right? And this silent symbol is up to the system designer, and we'll see in just a minute as to why you would want to choose this silent symbol a little more cleverly. Right? Instead of choosing something arbitrary, you can put a little bit of thought and see why you may want to choose a particular silent symbol. All right, but this is basically what you do in TDMA. Now, although I'm calling it TDMA, essentially this is the same as what you would do even in say frequency division multiple access. As long as you have these resources, these channel uses are something completely abstract. They need not necessarily be n time slots. They could also be a combination of say time slots and frequency slots, and 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 all that we need is that the channel is operating independently on each channel use, right? It's a memoryless channel. So in practice, when you're actually translating these notions to what is there out there in the field, each channel use could correspond to maybe n time instance, but it could also correspond to say n frequencies, right? And that is it's completely up to how the rest of the system is being designed. All right, so more generally, this is what we call okay, so I will call this TDMA, time division multiple access. All right, and we'll see that is a little different from what I call a time sharing scheme, because a time sharing scheme will sort of generalize TDMA. Okay, but TDMA refers to that scheme where one user transmits is active in by which I mean that it transmits a code word which depends on the message, whereas the other user is silent. It is transmitting absolutely no useful information in those channel uses. All right. Any questions? But note that in all the n channel use, the channel is behaving in an identical manner. So for every I, P of yi given x1i, x2i is always the same.
Sir, we are unable to hear you.
Sorry. Yeah. So let us see how TDMA performs. Right. So at one extreme, you could have say one user being silent all the time, whereas the other user is active all the time. Okay. And in that case, what is the best that user? So let's say that user one is active, whereas user two is completely silent all the time. Okay, then it just essentially reduces to sort of just a point-to-point channel. So then, what is the best rate that you can achieve?
Entropy, we can say, sir.
Why entropy?
The max, I mean, optimal kind.
Yes, this is a channel coding problem, right?
Yes, sir. Or else the maximum capacity which it can achieve.
Exactly. So exactly. So what would the capacity be? So you know that you are given P, Y given X1, X2. So this is the channel, right? So in some sense, it should be the maximum of some mutual information. But what mutual information do you think this is going to be? So note that X1 is transmitting all the time, whereas user 2 is silent. So suppose there was no X2. Okay? So the channel was Py given X. All right. So in this case, what is the maximum rate at which you can transmit?
I of x y
Correct. So it's the max of
max of
over Px of I of
yes,
xy. Correct.
yes.
But now it's not just Py given X. There's also another X2. Right? So then it would be some I of x1 y given x2, right? Because you're fixing some x2, right? So in fact, the maximum rate at which user 1 could transmit would be I of x1 y given x2, and remember that you're fixing x2 to be some silent symbol, right? So this is really the silent symbol. And in particular, depending on what P of y given x1, x2 looks like, you may want to choose this silent symbol in a clever fashion. So you want to ensure, you want to choose that x2, the silent symbol to be that x2, for which this mutual information is as large as possible. Right? So really the maximum rate at which you can transmit is max over both px1 as well as x2 of the mutual information between x1, y, given that x2 equal to little x2. So that would correspond to the rate point over here. Right? So this would be C1. Now similarly, if user 2 were active all the time and user 1 were silent all the time, then the maximum rate at which user 2 could transmit is given by this quantity. Right? It's the maximum over all possible x1 and px2 of the mutual information between x2y given x1 equal to little x1. And that would give us some rate point C2. Right? So you know that this is achievable and this is achievable. So obviously, if we want to suppose that, say, suppose user 1 was active for alpha fraction of the time and user 2 were active for 1 minus alpha fraction of the time, then for alpha fraction of the time, really user 1 should be operating at a rate C1 and user 2 should be operating at a rate C2, right? Because after all, in the time that you are active, you should be talking as much as possible, right? So the effective rate that you can achieve is alpha C1 and 1 minus alpha C2 because you're talking for only alpha fraction of the time, right? So therefore, what set of rate pairs are achievable? So if you used TDMA and you varied alpha between 0 and 1, what would be the set of achievable rate pairs? What would that look like?
A straight line joining these 2 points.
Correct. So it would be some straight line joining these 2 points. Let me call this C2. Okay. So this is what you would get if you used TDMA. All right. So let's see one particular example. Okay. Let's see something which is not an additive MAC. Okay. So this we'll see is another sort of MAC, but maybe this will tell us what one can. Right. So it is this sort of MAC where you can choose where the input alphabet is kind of constrained. So let us assume that user 1 and user 2 can transmit only binary symbols. So it can either transmit 0 or it can transmit 1. Okay. So in some sense, a user can either be on or off in one particular time instant. Right? And the receiver receives a symbol y, which is the sum of those two. This is the real sum of those two. So the output can be either 0 or 1 or 2. So if both user 1 and user 2 are transmitting 1, then the receiver gets 2. Okay. So in this case, what is C1 equal to? What is the max? So suppose that x2 is equal to 0. Right? And then what is the maximum of the mutual information between x1 and y? So x1 is either 0 or 1. You can look at all possible distributions on x1. x2 is fixed, it is equal to 0. So in this case, what would be the maximum of the mutual information between x1 and y, given that x2 equal to 0?
One minus H2P.
Why is it 1 minus H2P?
Sir, we are considering only X1 and Y when we are not considering H2 this time. Maximum capacity.
So now suppose that x2 is 0, right? 6 would equal to 0. So what is the relationship between x1 and y?
So this will be only.
So what is y equal to?
X1.
It will be just I of x1 y. Can you say?
What is I of x1 y equal to? Okay, so let's write this down. Okay, so what is the mutual information equal to in terms of entropies? Yes. So what is the mutual information in terms of the entropies?
Can you say h of x minus h of x given?
Okay. So h of x1, of course, given x2 equal to 0, minus
h of x
x1
given y.
Given y and
x2
equal to 0. Okay. So what can you say about the second term? Okay, so first term, what is this equal to? x1 is independent of x2, right? x2 is fixed anyhow.
Only H of x1.
Correct. So this is h of x1. Okay. What about the second term? What can you say about the second term?
This will be 0, so y is already.
Yeah, so y is equal to x.
So
So
this
h
will
of x1 given y and x2 equal to 0 is 0.
yes.
Right? So the mutual information is just equal to the entropy of x1. So what is the maximum of, so you want to maximize the mutual information over all possible px1.
Yes.
So what is that equal to? Yes, what is the maximum of the entropy? Come on.
One minus p, something like that, for binary erasure.
There's no binary, there's no erasure, nothing over here, right? So you just what is the maximum of the entropy, right? For all possible input distributions. So you know that x1 is binary.
So,
So when is entropy maximized?
so positive symbol is weak. I equal like
Sorry, the probability of symbol.
like 0 and 1 is probability will be equal, like g equal probability of
Okay,
0
so it's
equal.
when the input is uniform, right?
Yes.
And what will the entropy be equal to? So you know that x1 is binary, right? So it's can take only two values, 0 and 1. But you also know, as I just said,
That will be
entropy is
once.
maximized when the input is uniform, when x1 is uniformly distributed. So what does that, so what will it be equal to?
So it will attend 1.
Exactly. So it's just one bit, right?
Yes.
Right. So the maximum mutual information is when you pick x1 uniform, it's Bernoulli half, and x2 is anyway you know that it is equal to 0. So c1 equal to 1 bit, and c2 similarly in a symmetric fashion. If x1 is 0 and you're maximizing the mutual information over all possible px2, then c2 is also equal to 1 bit, right? Okay. So now what if x2 equal to 1? x2 is not equal. So this maximum of the mutual information, you maximize the mutual information, but now take x2 equal to 1. So the silent symbol is not 0. So when user 2 is silent, it always transmits symbol 1. Okay. So in this case, what is the mutual information equal to?
So again, sir, output will be just reverse of x1, whatever we are transferring, because y equal to x1 plus 1.
Yeah, so y is equal to x1 plus 1. So given x1, y is a deterministic function of
Yes, sir.
x1.
That
And
will be
similarly, x1 is a deterministic function of y. So h of x1 given y is equal to 0.
yes, sir.
Similarly, x1 is independent of x2 anyhow. So therefore, the h of this mutual information is still equal to the entropy of x1. So the maximum mutual information is still 1 bit. Okay. So now, at least for this channel, which I call it a binary erasure MAC, whatever, it's an additive MAC. It's a binary input additive MAC. Now for this particular channel, both C1 and C2 are 1 bit. Right? So this would be 1 bit and this would be another bit. And you know that this is achievable. In fact, any rate pair in this particular region is achievable, right? Because any rate less than capacity can be achieved. Okay. So we know that this is a simple bond, and so any set of achievable rate pairs. So any set of achievable rate pairs gives what is called an inner bond. So an inner bond is sort of something like a lower bound. You know that the capacity is at least this. You know that certainly every rate region is in this region is achievable. And obviously this is going to lie inside the optimal rate region, and that is why we call it an inner bound. Now at the same time, we also want an outer bound. So what rate regions we definitely know are not achievable? So the actual capacity region is going to lie inside some particular region, and then that is given by an outer bound. So ideally, we are happy if the inner and outer bounds exactly match, but that in general is not possible, right? So okay, so let's look at outer bounds, right? So certainly, I claim that so certainly R2 can never exceed C2. Do you agree? So R2 cannot exceed C2, and R1 can never be greater than C1. No matter what you do, no matter what coding scheme you use, R2 cannot be greater than C2, and R1 cannot be greater than C1.
Yes.
Do you all agree?
Yes.
Okay. So certainly, let me. So these regions cannot be achieved no matter what you do. Okay. So definitely, for a rate pair to be achievable, we must have R1 to be less than or equal to C1, and R2 should be less than or equal to C2. Okay, so let us see if we can get some other kind of an upper bound. So just like we did in the Slepian-Wolf case, suppose that we merged encoder 1 and encoder 2. So that is obviously more powerful than the current setup, right? So suppose that encoder 1 also knew what M2 is and encoder 2 knew what M1 is, so that you could do some sort of combined encoding, which is actually not possible. Right? So even if you merged the two encoders, then what can you say about R1 plus R2? So even if we combined encoder 1 and encoder 2, so that we had this sort of setup, M1, M2, X1n, X2n. You give this as input to the channel. And to the decoder, right? So if you can achieve some particular R1 and R2 over here, sorry, if you cannot achieve some particular R1 and R2 over here, obviously you cannot achieve that particular rate pair for the multiple access channel, right? Where you had two separate encoders, because that is obviously the encoders have less information, right? So for this, what can you say about R1 plus R2? Can you say something in terms of the mutual information involving X1, X2, and Y? Did you use the point-to-point channel coding theorem in some way?
Mutual information of X1Y and X2Y. Can we say that, sir? Unable to hear you, sir.
Not really. So you're combining the two, right? So it's as though you're transmitting a total of n times R1 plus R2 bits. So effectively, the combined message has n times R1 plus R2 bits. And in each channel use, you're transmitting two symbols, right? Which is X1 of I and X2 of I. Correct? So this is your kind of super symbol, right? Let's call it X bar of I. So you're transmitting X bar of I in each channel use, and you're seeing a Y of I at the output in each channel use, right? So what can you say about R1 plus R2?
Mutual information of X1 plus X2 given Y, something like that.
Not X1 plus X2, right? You don't have X1 plus X2. So it's just the X1, the X2 of the mutual information between X1 comma X2 and Y. Because this is a super symbol, right? It's a concatenation of the symbols X1 and X2.
Yes. Okay, sir.
Right? So in each channel use, you're transmitting two symbols, X1 and X2, and you're observing one symbol at the output, which is Y. Right? So this is if you had, of course, a common encoder for both. Right? So that gives you some particular, so let's call this C12. Right? So we know that C12, so any rate, so the sum rate should be less than or equal to C12. That corresponds to this. Right? So this is effectively C12. Okay, so the outer bound gives us some pentagonal region. Right? So we know that the set of achievable rate pairs should lie within this region, but we don't know if all of these rate pairs are achieved. Right? We know that everything outside this pentagon is not achievable. So the gray area is completely not achievable, but we know that the green region is achievable. We know that everything in the gray region is not achievable. Everything in the green region is achievable using TDMA. So the question is, what about in between? Right? Are some rate pairs achievable in this region? Are some rate pairs not achievable in this region? And that is what we'll see in the next couple of classes. We'll in fact see that the achievable rate region, actually, you cannot, in general, you cannot achieve the entire pentagon, and you can strictly do better than TDMA. But the rate region will turn out to be some complicated region which looks something like this. All right. So within this, we'll show that this region is achievable. The black region is achievable using something better, but there is some region in between the pentagon and this weird looking shape over here, which is not achievable. All right. Okay, so we'll stop at this point. Any questions? Okay, so if there are no further questions, then we continue tomorrow.
Thank you, sir.
Right, thank you.